Focused. This is your one warning on not talking while I'm going through this problem. So everybody, earbuds out, pay attention, and your next warning for not talking will be removal from the class. Is do not have the time, energy, or want to sit there and tell you guys to be quiet 15 times. That's right, I'm looking at you. So where did we leave off yesterday? Specifically, what were we doing? I know the pyramid problem. Okay, so we just figured out that if this is 147 and this is 52, that the distance the block is sliding is 187 meters, right? Now, I'm going to back up a little bit to make sure everybody's on the same page. Remember that what we were doing was that we got to this point where, using the transitive property of equality, we said that the net force times distance is equal to our final kinetic energy. Everyone remember that? And this right here, that's what we're looking for. So the first thing we did was find our distance, or a displacement. The block is going to slide down 187 meters worth of pyramid, right? So now we need our net force. Now our net force, and hopefully one of the things you guys need to understand is that everything we do in this class is going to come back, okay? So in doing this problem, we are using skill sets like we used, sine, cosine, and tangent. We've been using that to solve triangles since September, right? We're now going to be breaking down force vectors, specifically gravity. So remember, when we have this block, this 13-ton block, sliding down the pyramid, the only portion we're trying to figure out how much of, because we know gravity works this way, right? So what we're trying to do is figure out how much of gravity is working down the pyramid and what else will affect how quickly it's sliding down the pyramid. Think about it this way. Friction. Perfect. Good job. And we know friction is going to resist that slide. So our net force down the pyramid is going to be equal to the force of gravity parallel to the pyramid, the direction of travel, minus the force of kinetic friction. That makes sense to everybody? And again, this is stuff that we did back in our force unit. Now, hopefully you guys remember that force parallel, the way we figure that out is we take the force of gravity and we multiply it by the sine of the angle of the ramp. The force of gravity is mass times acceleration due to gravity times the sine of theta. Now, if you looked back at what we wrote down for all our givens, am I going too fast? Yeah. Okay. If we look back at what we wrote down for all of our givens, you'll see that we have m, g, and theta already filled out. So now it's just a matter of plugging those in. So that's 1.37 times 10 to the 4th kilograms. That's our mass. We know acceleration is 9.81 meters per second squared. And we know that our angle is 52.0 degrees. Notice all of these have 3 sig figs. Well, acceleration, this doesn't count when it comes to significant figures. Okay. So run that through a calculator. You guys need, specifically this times 10 to the fourth, you guys need to know how to do that. Huh? Times 10 to the sixth? Or fifth? Fifth, okay. Okay, so if you have a calculator, you're going to hit 1.37. You're then going to hit the second button. There are different ways of doing it. This is how I like to do it. Second, and then you're going to hit the comma button. That's the one directly above the 7. And then you're going to hit 4. Now, what's going to pop up on your screen is this. And remember that E is the same thing as times 10 to the. Okay? And then times 9.81 times sine 52. Now, you actually don't even need that. You can also just go times 9.81 sine 52. Your calculator, when you put a number right next to sine, will read that as multiplication. I'm kind of 50-50 each way. And what do you get? You get 1.06 times 10 to the 5th, I believe. Huh? What'd you guys get? So you got 105,000. What? 906. So we get 3 sig figs. So that's 106,000. 1, 2, 3, 4, 5. 1.0. That was interesting. Which then turns into 1.06 times 10 to the 5th. Why is it to the 5th? Because of how many times yeah. So if we're, yeah. How did I get 1? Because you're probably, are you in radians or degrees? Hit mode. Yeah, switch it to degrees. Now, don't re-enter the problem. Just when you go back and hit clear, hit enter again, and it'll recalculate it with degrees. Okay. Are we pretending that we see better from there today?
I actually like sitting here and you can like talk this.
Okay. That's fair. Okay, so does everybody know how to get that on a calculator? Okay, so do you have a calculator? Okay, so what I want you to do, see that those keystrokes up there? 1.37, hit the second button, that's the blue button on the top left. And then you're going to 5, 4, 3, 2. Oh, yeah, I know, right? I'm just joking myself into having to reset everything. So if you hit that 1.37, when you hit that blue button, that second button, what that means is the next button you hit, instead of doing the primary function of it, it'll do whatever is written in blue above it. You see how in blue above it says EE? So that means times 10 to the. It's just a way of writing that in science. So what you're going to do is you're going to hit that second comma and then 4. And what it'll show up on your screen is 1.37 e to the fourth, which is the exact same thing as 1.37 times 10 to the fourth. Yeah, you may. Okay. So again, the reason I want to make sure you all know how to do this is because there will be problems like this on any upcoming CFA or test. And I want to make sure that when we're doing those tests or CFAs, that what's being tested is not your ability to use the calculator, but your ability to solve the problem. I don't want to be like, hey, Mr. Renard, I know how to do the problem, but I can't do it because of this stupid calculator. Does that make sense?
So now that we do that times.
No, so this right here in newtons, that's my force parallel. That's the gravitational pull of the object down the pyramid, okay? So what we're going to need to do now is we're going to need to find the kinetic force to be able to subtract from that. Yes?
Wait, how is that the parallel force if we just did the force of gravity? Isn't that the difference?
Times the sine of 52. That sine of 52. So do me a favor, just hit 1.37 times 10 to the fourth times 9.81. Enter. That's the full force of gravity.
Okay, so wait, when you wrote, because you wrote f of g sine 0, and
Right.
right under you wrote f of g sine, or m times g sine 0.
That's because the force of gravity is equal to the mass of an object times acceleration due to gravity.
Oh, okay. I thought you were saying all that second line was just f of g.
No, those two, and then this stays the same. Okay. So then over here we have the force of kinetic friction. Now we know that the equation for that is the force of kinetic friction equals normal force times the coefficient of kinetic friction. Again, this is one of those things that we learned several weeks ago, but you guys are then going to have to reuse time and time and time again. Okay? Now remember that normal force is always going to be perpendicular to the surface, right? So when we put something on a ramp, the normal force decreases. In this case, and I hope you guys remember this, normal force is going to equal the force of gravity times the cosine of theta, which would then be mass times gravity times the cosine of theta, which means that our friction, sorry, let's make this a little bit bigger, that our force of kinetic friction is going to be mass times gravity, that's the full force of gravity, times the cosine of theta, that's the force of gravity actually pushing the block against the side of the pyramid, times the coefficient of kinetic friction. And we have all of those, right? We know mass is 1.37 times 10 to the fourth kilograms. We know gravity is 9.81 meters per second squared. We know that our angle is 52.0 degrees. And we know that our coefficient of friction is 0.45. So that you want to drop into a calculator. Now here's the thing. I'm going to be honest with you guys. When I do this on a calculator, I would either put the 0.45 at the beginning or do this part, hit enter, and then go times 0.45. The reason is I always get a little worried when I have something like cosine 52 times 0.45? Because I worry that the calculator is going to do the multiplication first and then take the cosine of that answer. So I either hit enter in between. That's not how you spell enter. Good job, Bernard. Or I just hit 0.45 cosine 52. Either way, you're going to get the same answer. So, what do we get for that? So what is the actual number that comes out on your calculator? 37,234?
No. Like two, I don't know, there's like six, I don't know.
Okay, let me see.
Like 6 or 2, it's like 2 million or something.
I don't know what happened. That's what I got.
Okay. You're right, Rory.
I'm not sure what happened. Like, I tried to figure out what happened the other time. I'm not sure. Like, it looked like you entered it correctly, so I was confused as to what happened. So this, remember, we get 3 sig figs here, so this is going to be 3.72. 1, 2, 3, 4 times 10 to the 4th. Okay? So that's our force of kinetic friction. So we know, hold on just a second while this catches up. So we know that our net force So our net force is going to equal 1.06 e to the 5th newtons minus 3.72 e to the 4th newtons. Oh, looks like they're gone. So drop that in the calculator. What do we get?
Never mind.
Okay. So what do we get? Now remember that what we started with was our final kinetic energy being equal to our net force times the distance applied. So that's going to be 6.88 e to the fourth times 189. And notice that we end up with Newton meters, which is what joules are. Shh. Is it 187? Okay, sorry. Final kinetic energy. What do we get? Go. 1, 2, 12 million, what?
865,000. 600. What are you?
Does that make sense? Hello? Absolutely. Bye. Stephanie, you're getting checked out. Have a wonderful day. Okay. Shh. Okay, so you guys, listen up. Hey, that's the problem.
Wow.
It is. So here's the thing.
That's like one whole picture.
Yep.
For one dollar.
I could chug it up.
So listen up. Hey, shush. Stop complaining and listen. Good job. That looks pretty. Okay, you guys, here's the thing. The primary point of taking a science class in high school is not necessarily to make you experts in the subject area. Okay? It's to expose to you that these things are out there. And also, science is a fantastic tool for teaching you guys how to think better. It improves your rational thought. It improves your problem-solving techniques. And those skill sets are available or applicable everywhere. Hey, talk and be quiet. So, shh. Literally, I just yelled at other people for talking while I'm talking. Like, at least wait 3 seconds. So here's the thing. Was there any expectation that I could drop a problem like this in your laps and you guys would just be able to go right through it?
I bet some of us.
Absolutely not.
Not me. I'm not saying.
Shh. Okay? Is there the expectation that you guys should be able to look at this and follow along with what I did, assuming that you're actually paying attention to what's going on and not just blindly copying down what I'm putting on the board? Yes. You should be able to look at this and go, okay, we started off drawing a picture, writing down our knowns and unknowns. We then sat there and went, okay, what equations can we relate to each other? So we started here. Remember, this was the definition of work. And this originally was, yeah, this is up top. So this was the definition of work right here. And this right here is the work kinetic energy theorem. We realize that if we have the block starting at 0 velocity, then that means that any work done is going to be equal to the final kinetic energy, right? Because there's 0 kinetic energy at the beginning of the problem. We realized that meant the final kinetic energy is equal to the work done by the block sliding down the pyramid. Well, work is equal to net force times displacement. We figured out what the displacement was. Net force. How much force is pushing it down? How much force is resisting it? These are all things we've done individually, right? And I know sometimes putting them all together and expecting you guys to do all of it at once is a lot, but that is where we're aiming, is for you guys to have this toolbox of equations and skill sets that you can use to pick apart a problem like this. So it's important that when you guys, and I'm going to be honest with you, if you guys actually reviewed your notes like you were supposed to, you'd be a lot further along. Because look at the skill sets that we used here. All of this stuff should be in your notes. How to solve for the missing side of a triangle. How to figure out the force of gravity. How to figure out the force of gravity pushing down a ramp. How to figure out the force of kinetic friction resisting that. All of this stuff is stuff we've done and you've taken notes on. But when you aren't engaging with your notes, when you view those notes as something you do just to keep me happy, instead of going back and realizing that what they are is a way for you to understand what we're doing and apply that in the future, you guys are hamstringing yourselves. Okay? So, my advice to you would be to take this, look at it until you understand it.
That's gonna take me like 2 years.
Disagree.
I don't.
That's okay. It's just because I have more faith in you than you do. So, you guys, this is where we started, right? So, potential energy is energy stored due to an interaction with the surrounding. The two that we're going to be talking about are elastic and gravitational. Okay? So, Yeah. So, here I have two balls in my hand, a softball and a bowling ball. Caleb, put your hands out on the desk.
Oh no.
They're from the same height. Which one do you want me dropping? So why?
Because it will hurt a lot lighter.
It's a lot lighter, right? And that's because when we look at our gravitational, it is... Shh. There are two things. See? This is why I say you're capable, but you won't shut your mouth. So, there are two things that affect gravitational potential energy. Mass and height. What if I were to drop it from here? Here, nothing really happens, right? If I drop it from the same height, little bounce. Bigger bounce. If I threw it all the way up, even bigger. Okay? So we'll pick this up tomorrow. Have a wonderful day, everybody. I'll see you guys then.